So 9.4. In 9.3, let's just go back a little bit. 9.3, we talked a whole lot about exponential functions. We talked about kind of what they look like if it's exponential growth, what it looks like if it's exponential decay. And now we're kind of talking about the opposite of exponential functions, which are logarithmic functions and how they relate to each other. So just like if I said, what's the opposite of addition? You're going to tell me subtraction. If you're in algebra and something's added on and you need to get rid of it, you're going to subtract it. Those things go together. If I said, what's the opposite of multiplication? You would tell me division. Same thing. If you were doing an algebra problem and something was being multiplied and you needed to get rid of it, you would divide. Same thing with if I said, if I have an x squared and I need to get rid of it, you would take the square root, because something raised to the second power and the square root, they undo each other. So this is similar. Something that is exponential, an exponential and a logarithmic function are opposite of each other. They undo each other. So you really can't go into talking about one of them without the other. So on 9.4, we're really learning about, on this one, how do you type this stuff in the calculator, and what are some of the properties of a logarithmic function, and how does it relate to an exponential function? So these are some basic properties that we'll discuss about the I guess the hows and whys a little bit more in 9.5. But for today, we're kind of I guess I would say scraping the surface. We're just looking at what they are on the surface. So this is, of course, an exponential function. This is like what we talked about in 9.3. And an exponential function always has x as an exponent. So this would be an example of exponential growth, because we're starting out really, really small and we're getting really big really fast. Okay. The other one would be like 1/2 to the x power, which would be exponential decay. So we already went over this in 9.3. All they've done is graph it for us. Okay. And so I'm going to take, just because I want you to be able to see it down here, I want to take and plot some of these points for y equals 2 to the x on this graph. I'm going to make them blue. So one of the points would be 0, 1. So the blue is going to be y equals 2 to the x. Okay. If I plug in 1, I would get 2. If I plug in 2, I would get 4. And this graph kind of looks something like this. It's the same one that you can see above. Does something like this. And when you graph it, it gets really close to the line x equals the x-axis, or y equals 0, but it doesn't touch it. So that's that line, y equals 2x. We're going to talk about this a little bit more, but for right now, how is this blue? And in a minute, I'm going to graph this other one in, let's say, green. So how is this line, how are these two things related? If we wanted to compare just the two equations, y equals 2 to the x and x equals 2 to the y. What have we done? We switched the x and the y, right? That's all we've done. The 2 didn't change. Wherever we have a y, it was an x, and wherever we have an x, it was a y. And that is called something special. That's that they're inverses of each other, which is what I just got through saying. This is actually, it's written in an exponential form, but it is the version of a logarithm, and we'll talk about why that is in just a minute. But these are inverses of each other. So if I want to graph this and my equation is x equals 2 to the y power, well, the only way I'm going to be able to do that is if I plug things in for y. If I kind of work backwards and plug things in for y and figure out what x is. So they already told me what all the y's are. I just need to figure out what the x portion is. So they're telling me why plug in 0, plug in 1 for y, plug in 2 for y, plug in 3, plug in 4. No, Miss Hill's not reading today. Plug in -1, plug in -2, and plug in -3. So if I go to my equation up here, 2 to the y, they're saying find what happens if you plug in 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the -1, 2 to the -2, 2 to the -3. And we talked about last time on 9.3, some of these properties. I'll go over them a little bit again, but anything raised to the 0 power is 1. 2 to the first is 2. 2 to the second means 2 times 2, so 4. 2 to the third means 2 times 2 times 2, so 8. So far we've got 1, 2, 4, and 8. We figured those out. I'm going to go ahead and plot them. 1, 0, 2, 1, 4, 2. I'd have to go off the graph to get to 8. So this would be 6, 7. This is 8. 8, 3. Okay, if you have a negative exponent, then what that property tells you to do is you're going to put a 1 on the top and then move 2 to the first to the bottom. So that would just be 1/2. This one is going to be 1 over 2 to the second. So that's 1/4. 1 over 2 to the third, 1/8. So we've got these points, 1/4 and 1/8. So I've got a point at 1/2, -1, 1/4, negative, I'm sorry, 1/4, -2. Sometimes when I do these backwards like this, I forget that I'm on my x-axis, not my y-axis, but, and then 1/8, -3. So this line gets really close to the y-axis, or this function gets really close to the y-axis, but it doesn't ever touch it. So this is x equals 2 to the y. This is going to be a logarithm. It's just written in exponential form. So if you look at these, you can kind of tell that they are reflections of each other. Like if I draw a line right through the middle right here, if you fold it on this y equals x line, they would touch each other. Y'all agree with that? So some interesting properties about the exponential function is, well, it never gets below the x-axis unless you say minus something and push it down on purpose, right? It's bounded by the x-axis. On the logarithmic function, it's bounded by the y-axis. So if I plug in a negative, something negative for x, it wouldn't have any values because you don't see any green on this side of the graph. Okay, so that's going to be something that's kind of, it's going to be something we'll need to pay attention to. Okay, so the next part of this says to find the formula for the inverse. We just got through graphing this, y equals 2x, and then we compared it to the inverse. So they're saying take your, so they're wanting us to find the inverse of the exponential function 2 to the x power. We've already done this step, these steps. This is kind of a review. If I want to find the inverse, the first step is replace f of x with y. So I say, okay, well, y is equal to 2 to the x. Then the next step is interchange x and y. So that means that x is equal to 2 to the y, which is what we just graphed, this red line. Okay, now here's where the logarithm comes in. If I want to solve it for y, I have to use a log here, and we're going to discuss y and a lot more how to do this later. There's no homework problem on this that makes you do this. But in order to solve for y, I've got to get this y to come down. So I'm going to have to take the log of both sides of my equal sign. And the reason I'm doing that is there's a property that goes with logarithms that if you take the log, you can move your exponent down front. And that's going to help me. I move my y down front. I don't expect you right now to understand why we're doing this, okay? Because in 9.6 and 9.7, we go over, or 9.5 and 9.6, we go over solving these things a bunch. Okay, but we need our y to come down, and there is a property that says we can do this. Now I can solve for y because I can divide both sides by the log of 2. And so these log of 2's would cancel out, and I would get, well, y is equal to the log of x over the log of 2. And the last step would be to put replace that y with the inverse of x, log of x over the log of 2. Okay, so that's why I keep saying, well, those are just, they're inverses of each other, but this right here is actually the log of x over the log of 2. And you could shorten that too, but we're not ready for that. So we're going to move on, but that's how they're related, the exponential function and a logarithm. So log base 2 of x, you would read that the logarithm of x base 2. And I just read it differently. I always say the log base 2 of whatever it is, but you can also read it this way. And this means the power to which we raise 2 to get x. So this whole thing means that if we did 2 and we were asking ourselves, what power do we raise 2 to get x? That's what a logarithm means. When I was in school, like when I was younger, way younger, logarithms to me, I wish I had been able to back up and realize that it's just a definition of something, because to me it was like so abstract that I just couldn't get it, because I don't think anybody ever slowed down and was like, this is what this is all this means. Okay, so if when you look at these, it says if you look at the inverse of f of x equals a to the x is given by the inverse of log a to the x. So it kind of gives you a definition of how you can get from one to the other. If a is greater than 0, so like 2, 3, 4, 5, you're going to have exponential growth, and your logarithm is going to be upside down like this. That would be your inverse. If a is in between 0 and 1, like 1/2, you would have exponential decay. And when you do the inverse of that, your logarithm is going to be facing up like this instead, because you're reflecting it across that line. Okay. And once again, like a lot of this stuff, you're going to be able to look at on your graphing calculator. So it's not like you have to understand all the ins and outs about it, but you need to be able to make some connections. So we've got some basic properties when we are comparing exponential functions to the inverse of that, their logarithm function. Bless you. So the exponential function compared to the logarithm function, they're both continuous. They don't have any holes in them. Okay. They're also both 1-to-1. The domain of an exponential function is all real numbers, because this thing keeps getting wider and wider and wider. It's going to satisfy all x's. The domain of a logarithm, though, is all positive numbers. Remember, we talked about, well, it doesn't ever have all these x's that are negative over here. There's nothing on the graph that goes with those. So that's different. That is different. The domain of the exponential function goes with the range of the logarithmic function. And the domain of the logarithmic function goes with the range of the exponential function. So those are kind of opposites of each other. The range is going to be all positive numbers. If you look at your graph, we said, okay, this has to go, it's above the x-axis. And then on the range of the logarithmic function, well, this thing goes down forever and it goes up forever. So it would be all real numbers. They're both increasing. So that stays the same. These are opposite. This one has a horizontal asymptote and it's the x-axis. And this one has a vertical asymptote and that's the y-axis. Okay. And this is kind of weird. This one has a y-intercept, but no x-intercept. And this one has an x-intercept, and this one has no x-intercept. So that part's opposite of each other. So if you're just kind of comparing the two functions to each other, they've got some things that are kind of directly opposite of what would happen to the other one. We define y equals log a of x as the number y such that x is equal to a to the y, where a is greater than 0 and a is a positive constant other than 1. We're fixing to talk about what all that means. And we read log base a of x as the logarithm of x base a. So this property, I do want to slow down for just a minute. On this property right here, I like to write it with the log in the front. So the log base a of x is equal to y. And on this one, I like to write this with the exponent part in the front. And I'm going to show you why. In this section, you're going to be forced to move these back and forth a lot from exponential function to logarithmic function. And from logarithmic function back to exponential function. And if you write them this way, I feel like it's easier to kind of go back and forth. So here's what I tell students to do. This is obviously your logarithmic function. If they tell me to write it as an exponential function, that means they're asking me to write it like this. I always go to my first number. In this case, it's actually a letter, but the first thing that's not a log, and I start there. Then I skip the next thing that should be a number or a variable. I skip that and I go to past my equal sign to the y, and then I come back to the x. So I kind of do a circle around, and then I say, okay, well then I write down the a, and then since I skipped the x, I write down y is equal to whatever I come back to, which is x, which is exactly what we have right here. It's just kind of, and we're going to go over that a bunch here in just a minute. But that's just kind of I guess, a memory tool that helps me write these back and forth without having to go back and look at the definition over and over again. So on this one, this is written in exponential form. I know that because it has an exponent in it. So if they ask me to put it back in the logarithmic form, I would start with the first thing. I would skip over the equal sign and come back. Same pattern. Start with your first thing, skip over the equal sign, come back. Start with your first thing, skip over the equal sign, come back. So that means that if I want to put it in the logarithmic form, I'm going to have to write log. And then the first thing was an a. I skipped over the equal sign and I got an x. Then you go past the equal sign and you write your y, which is exactly what we had. So if you'll do that skip over thing, it kind of helps. Here's a couple of examples of that. So they wrote down, I'm working this problem right here. So they wrote down log base 10 of 100 equals 2. So if I was working this, I would say, well, I'm going to start with it's written in logarithmic form. So I'm going to start with my first number. I'm going to skip over the 100 and then come back to it. So if I want to write it in exponential form, it would be 10 raised to the second power. So I'm skipping over the 100 and I'm coming back to it, is equal to 100. Those two statements, these mean the same thing. So on this one, they're starting with another thing that is very similar to a logarithm. Ln just means the natural log. And if you see Ln, E is always your base. So Ln base E of 5, and they're telling me that's equal to 1.609. So I would It's written in logarithmic form, even though it's a natural log, it's the same concept. So I would start with my base, skip over the 5, and then come back to it. So I would say, okay, well, then this means that e raised to the 1.609 is supposed to be equal to 5. Okay. It's just a pattern that you're going to follow. If they write down, or if you see a problem that just says log of, let's just do log of 25, and there's no number right here. A lot of times you'll see a number already there, but if there's no number right there, the number is automatically a 10. So that's just the normal logarithm would always be a 10. It's kind of like something that's understood. The same thing that you would do if you said, well, if I wrote down a problem and I have x plus 3, you know that that's 1x plus 3. If a logarithm doesn't have a base, you know it's base 10. ln will probably almost never have anything written here because every single time it's supposed to be e. We talked about e a little bit last in 9.3, but it's always e. So if there's nothing written there, it's an e. Okay, so there are a couple of ways to do this. So it says to use the log base feature on your calculator to work these problems and round them to 4 decimal places. Okay, there's another formula called and I'm going to write this, so the log base formula, because there are some problems on your calculator that ask you to use the log base formula. I want to write it right there because it's going to be too squished. Hold on a minute. So if they ask you to do the log base formula, what they're asking you to do is find the answer using a formula where you write the biggest number on the top, so the log base 8 over, not the log base 8, the log of 8 over the log of 2, and you divide those, and it would give you the answer for this problem. If I wanted to do this one, I would do the log of 1, because that's my big number, over the log of 6. This one would be the log of what? 3 over the log of 9. This is using the log base formula if you work it this way. I'm going to show you the other way as well, but log of 8 over the log of 8. What should the answer to this one be? Should be 1, right? Log of 8 divided by log of 8, same thing, but divided by the same thing. So when we go to our calculator, let's work these both ways. There's a button that we can push in our calculator to do these too, but make sure you know both ways. So sometimes you might not have a nice fancy calculator that has a log base formula, so you want to have another method. So on this problem, log base 2 of 8, we said we could do, so the log button is in the very first row, and so it doesn't have a base if we're using the change of base formula. So I would do just the log of 8 divided by the log of 2. I'm going to hit enter, and it tells me the answer is 3. Okay, the other way I can do this on the calculator is that I can go to my math button, and I can scroll all the way down to where you see log base. So I went to math, I went to log base, I hit enter, and then it lets me just type in exactly what I had, which is really nice. And I hit enter and it tells me it's 3. So it's 2 different ways for doing the same thing. The second one's a lot easier, right? Because you just type it in. The problem is that a lot of times later in life, or if you were taking a different math class, you may not have that feature on whatever you're trying to use. So you can also use your change of base formula. So we could go through the rest of these and work them. Log base 6 of 1, log base 9 of 3. See if y'all can come up. You can use this math, use your math and log base to do these. If you're following in chat or you're following in Zoom, go ahead and calculate. Let me go back to the page so you can see. So type in chat what the log base 6 of 1 is, and at least do these two, log base 9 of 3. We found this answer and we got 3. What are y'all coming up with a log base 6 of 1? I'm sorry, what? 0, yes. Log base 9 of 3. 0.5 or 1/2, either way you want to look at it. Okay, so the other way to go about this is, and I'm just trying to bring this up because I think the more times you see it, the better. If I were to write this in exponential form, so remember where that trick where we said start with the first number, write the answer, and then go back. So 2 to the third, is that equal to 8? Because that's what this means. It's just written in exponential form. This one is 6, skip over the 1, come back to it. So that would be 6 to the 0 is equal to 1. That's true because anything raised to 0 is 1. If I do this one, this would be 9, and I'm going to write the 1/2. So 9 to the 1/2 is equal to 3. Well, we haven't talked about this in this class, but if you raise something to the 1/2, it means you're taking the square root of it. So the square root of 9 is absolutely 3. We will talk about that some more, but we haven't gone over. And then this one is 8 to the first power is equal to 8. Right? They just go back. They're hand in hand. Okay. There are some special properties that if you see the log base a of 1, it's automatically 0. So anything, if it's like this log base 6 of 1, if this is because this is saying the answer is 1. Well, anytime the answer is 1, then you're raising it to the 0 power. That's why that is. The log base a of a is equal to 1. So if these two numbers are the same, like this 8 and 8, your answer is going to be 1 because they're going to divide out equal 1. Now you're always going to have your calculator that you can use and make sure, so you can still type this in if you can't remember that, but if you can remember it, it sometimes saves you some work. So they want us to convert each of the following to a logarithmic equation. When I do this, I always put the exponent part first, because then I can go and say, well, they want the log, so I'm going to start with, because you have, in order to follow that circle thing, you have to have the exponent part written first. So I start with the 2, I skip over my x and my equal sign, and then I come back to that second. It's either a number or variable there. So that would be the log base 2 of 16 is equal to x. It's always going to be equal to whatever that thing in the middle was, right? So this one's already written with my exponent first. So I could say, okay, this is the log. Start with the 10, skip over that -3, but come back to it. So log base 10 of 0.001 is equal to -3. Is that starting to kind of make sense a little bit now, or at least that pattern of following that? If you want to go backwards and you want to go from logarithmic to exponential form, you always want the log part to be written first, and both of these are. So we would say, okay, 2, skip over the 32, but come back to it. So 2 to the 5th is equal to 32. A to the W is equal to Q, because we're skipping over that middle term and then we come back to it. They're wanting us to do the same thing with this E. And remember that if you see an E, you automatically don't use log, you use the natural log. You're going to use ln instead of log, okay? So it says write each exponential equation as a logarithm or a logarithm as an exponential. So we're going to use the ln here. So right now this is written as an exponential. I know that because it's got a power in there. So it's got an exponent, so it's exponential. So I'm going to write ln because they want me to go back to the natural log. So I'm going to say, oh, skip over the t, come back to it. So natural log of e, natural log base e of 70 equals t. Same thing here. So this one would be natural log base e, natural log is always base e, of 4,000 is equal to negative t. Sometimes like this one, there's no answer over here. So if there's nothing there, put equals x because they want us to write it as an exponent. So if we don't have an answer, just put equals x. So e, skip over the 70, come back to it. So e to the x is equal to 70. This one doesn't have the base, but we know if it's natural log that the base is e. So that means that e, skip over the 0.38. So e to the negative 0.9676 is equal to 0.38. Okay, you good? So just like those other properties, if you get, because this would be e raised to the 0 power is 1. That's a property that you could memorize. You don't have to. You can always type in your calculator and they'll tell you. But if this is ln and both of these are e's, well, of course it's 1 because you're dividing ln of e divided by ln of e to figure out the change of base. So it's 1. Okay. So they're asking us to find the following common logarithms or natural logarithms on the calculator, round to 4 decimal places. So I'm going to go to my graphing calculator real quick and let's look at these. If you're following in chat, go ahead. So you should have 4 answers. I will go ahead and warn you that 2 of these don't have an answer, or it's going to give you something crazy on your calculator. So just put NA. So let's let this one be 1, 2, 3, and 4. If you're following in chat, let's type this stuff in and figure out what the answer to these things are. You can find the cube root under math. If you need to type in the cube root of something. So we've got the log of 645, the natural log of the cube root of e, the log of -3, and the natural log of 0. So and they're saying round to 4 decimal places. 2.8096. Is that okay with you guys? If I type in the log of 645. So that might have been confusing. If we were going to the log base formula, what would be the base on the log of 645? There's no base there. It's 10 then, right? If there's no number there, it's 10. But also there's an easier way. If there's no number there, you can just use this log that's on the very first row, because that's what this log is. Whenever they're assuming that the base is 10 here. So you don't have to use that thing under math on that one. You can just type in the log of 645. So that's how I'm coming up with 2.8096 if I round to 4 decimal places. The next one says the natural log of the cube root of E. Well, that is also on that main row. So I could do LN. And then to get the cube root, I can hit math and go down to 4 and hit enter. And this time we've got an e to the x above ln. That e, if I could possibly use that e, what power would I raise it to? If I use this little e to the x, I would have to raise it to the first power because I just have an e, right? There's also another e you can use that's above the division sign, and that one is not raised to any power. So that's the same, that would be, I could use that e and it would work. Some students have trouble remembering this one and can always remember that this is an e to the x there. You can always use that. You would just say e to the first power if it's not raised to anything. So arrow out of that and then hit enter. And it tells me it's 0.33333. So it would be 1/3. If we're rounding this to 4 decimal places, 0.3333, right? The log of -3. We talked about why this was, because there was on the graph, there were no values of x in the negatives. And we talked about the domain of a logarithm. It does not exist before 0, right? That's why on the log of -3, you don't get an answer. You can't take the log of a negative number. The natural log, so if we do the natural log of 0, also doesn't exist, because remember that y-axis x = 0 line, it gets really, really close to that, but it doesn't touch it. I'm going to go back and talk about that in just a minute, but new share. So we're going to have no answer for this one, no answer for this one, and this one was 0.3333. So if we go back and look, remember when we graphed the logarithm function was turned upside down like this. We didn't have any x's that were negative. That's why you can't take the log of a negative number. They don't exist. X = 0 would be this line right here. And this red line gets really, really close to that, but it doesn't touch it. So that's why you can't take the natural log of a 0, because doesn't exist. 0 doesn't have an answer. That's a vertical asymptote. Okay, here we go. So they want us to graph f of x equals the log base 5 of x. So if I don't have a graphing calculator, I'm going to have to change it to the exponential. So remember to change it to so this would be y = log base 5 of x. And I said always write the log first. You're going to change it back to an exponential because you would skip over and come back to it. So this would mean that 5 to the y power is equal to x, which is what they have right here. So they converted it to an exponent so they could actually graph it by hand. Very hard to do logarithms in your head. So they converted it to an exponential. So they've come up with some values for y. And they're wanting us to come up with, okay, what is 5 raised to the 0, 5 raised to the first, 5 raised to the -1, 5 raised to the -2. Well, anything raised to the 0 is 1. 5 to the first power is 5. 5 to the -1 means 1 over 5 to the first power, which is just 1/5. 5 to the -2 means 1 over 5 squared, which is 1 over 25. So we plot those points. We've got 5 to the 0. We have the point 1, 0. 5, 1. And then 1/5 -1. So it's going to be really close to -1, and 1/25. That's going to be really, really close to that y-axis. But remember that it doesn't touch it. It gets really close, but it doesn't touch it. There's never going to be a time when it goes over that y-axis. So that's how you graph that one. That's 5.4. On your homework,